Welcome back. In this video lecture, we will see another fluid property, which is called surface tension. So what is surface tension? By definition, it is which is in contact with a gas or on the surface between two immiscible liquids such that the contact surface behaves like a membrane under tension. So basically, it is going to be a tensile where the liquid interacts with the gas surrounding it, or it is going to be between the surface of two immiscible liquids. When we say immiscible liquids, they are not going to mix with each other, something like water and oil. Okay, so I just look at this particular diagram, focus your attention to this molecule A, and this molecule is completely immersed in water. That is taken as one example. And we can see that the forces which is acting on this particular molecule, they are balanced. The forces acting on this molecule, they are balanced. So the force on this particular direction, that is counteracted by the force on this particular direction. So they cancel out each other. Similarly, the upward force, that is counteracted by the downward force. Similarly, you can see that each and every force cancels out each other, and that is how this particular molecule behaves. So the forces are balanced. If you look at molecule B, the horizontal force towards the left and towards the right, it is balanced. But if you look at the other force, particularly the upward and downward force, this force which is acting in the downward direction seems to be a little bit more just because this particular molecule has not, it's not a complete circle. So a part of this molecule is an interaction with the free surface, that is with the air or gas that is surrounding it. So whenever we have a molecule that is very closer to the free surface, which is not just closer to the free surface, which is in connection with the free surface, then there you find that this tensile force, which is the upward and the downward force, they are acting in the opposite direction. So this tensile force exists, and that force is what we call as the surface tension. Okay, and look at molecule C again. So in molecule C, the horizontal force in the towards the left and right, they are balanced. However, you have only the force that is acting in the vertical direction. You have only the downward force and the upward force is missing, which means this is again an unbalanced force. So are the cases which are the forces which are acting downwards. They don't have another force that is acting in the upward direction to compensate them. So is the case with molecule B as well. Okay, so whenever we have this molecule that is very close, I wouldn't say very close, that is in interaction with the free surface, then that tensile force is what we call as the. So the magnitude of this force per unit length of the free surface, and it is going to have the same value as surface energy per unit area. Okay, the free surface of the liquid, it acts like a very thin film under tension. So it is look at this particular term, which is a very thin film, because it is going to be a very small layer, and it is on that particular layer the surface tension acts. So the surface of the liquid acts as though it is an elastic member under tension. Okay, so now let's look at surface tension in case of a liquid droplet. So assume we have got a droplet in a spherical shape, and let me divide this droplet or cut this droplet into two equal halves. There is one droplet on the left-hand side and there is another droplet on the right-hand side. And you can see that the droplet, which is on the left-hand side, on the circumference of this particular, surface of this half of the droplet, you can see that there is a force that is acting on the surface or the circumference. And this force is what we call as the surface tension. So surface tension is basically your, this is expressed in Newton per meter. Okay. And so this is your surface tension, which is denoted by sigma. And since this is acting on the circumference of this particular half of the droplet, then we can multiply it with the circumferential length times pi d. So that is one force. This is the force due to surface tension. This can be represented by sigma times pi d. And this is the force that is acting on the left half of your droplet. And then I have the right hand side of the droplet. This has to be, inverted. And if we look at the right hand side of the droplet, we will see that there is this pressure force which is acting on the cross-sectional, your pressure force. So the force due to the surface tension, that is going to be equal to, I can say either the pressure force or the intensity of pressure that is acting inside the droplet, the intensity of pressure inside the droplet. And this can be represented by, so pressure, obviously, we are going to represent it in terms of pressure P. And when you say intensity of pressure or the pressure force, so pressure is force per unit area. So if I'm going to call this as pressure force, it has to be multiplied with the area. And the pressure always acts on normal to the surface. That means perpendicular area of this particular droplet. So cross-sectional area of this particular droplet is circle. So we know that area of the circle is going to be pi by 4 d square. So these two forces, the intensity of pressure and the force due to surface tension, they are equivalent times pi d, and this has to be equated with pressure times pi by 4 d squared. Okay, and if I cancel out this pi and this pi, and to be consistent with the notation for the diameter, let's use capital D here as well, so that there is no confusion over here, because the diameter of the droplet is going to be capital D. So if you want me to write that, sigma represents surface tension. P represents the pressure, which is acting normal to the surface. Normal to the surface means perpendicular to the surface. That is what we mean here. And then capital D is the diameter of the droplet that is considered. So if I can cancel out one of the D over here, so my pressure P is going to be 4 times sigma divided by capital D. So this is the relation that we get for so sigma divided by 4. So this is what we see in case of a droplet. How about a bubble? So when I say a soap bubble, so here, when you would have looked at a soap bubble. So this soap bubble, it has got, the surface tension acting on both the surfaces. The inner surface of the bubble also has got air in it. So there is going to be on the inner side of the bubble, you are going to have one type of a surface tension force. And on the outer surface of the bubble, you are going to have another surface tension which is going to be acting on it. So you are going to have the surface tension force that is acting on this bubble on two sides. So in the previous case, we had the surface tension acting only on one side. So just like in the previous case, if we take the surface tension force, so surface tension force should be equal to the intensity of pressure inside the bubble. So in this case, extension is still going to be sigma, and it is going to act on the circumferential length. So we are going to multiply it by pi d. But unlike the previous case, now we have got surface tension both on the inner surface as well as the outer surface. So we have to say this is going to be equal to pressure multiplied by the area of cross section of this particular soap bubble, which is again pi by 4 d squared. So now if I could cancel out this pi and one of the d, I'm going to have pressure P is equal to 8 sigma divided by d. So this is the expression that we get as a relationship between the pressure and the surface tension in case of a hollow bubble. Okay, it's quite simple. The next one is surface tension in case of a liquid jet. So if you take a liquid jet that flows through a pipe like structure, and if I divide this into two halves, so you can see that the length of the jet is going to be L and the diameter of the jet is going to be small d. And you can see that if I split that into half, I have this rectangular cross section over here. And so you can see the surface tension force acting on the side of this particular rectangle. And so if I say the surface tension force over here, so surface tension force, and this is going to be along the length you have got the length on two sides. So this is one length over here. So this is L. And this is another length over here. You can see the surface tension force acting on both these lengths. So it is going to be 2L. L plus L is 2L. So that is your surface tension force. So you know that the length, the unit for surface tension is Newton per meter. And the unit for length is meter. So you have got the surface tension force. So that is how we say that it is the surface tension force. Okay. So now let's look at the other side. So the other side, it should be the pressure or the intensity of pressure inside the jet. So in this case, the area, so we have got pressure. And in the previous two cases, we have got area of cross section of a circle. Now we are having the area of cross section as a rectangle. So this is supposed to be L times D. This guy is this side of the rectangle is L and this side of the rectangle is going to be D. So it is length into breadth. So it is L times D. So now if I could cancel out this L and L, what I have got is P is equal to 2 sigma divided by D, or in this case, since the expression is that doesn't matter. Okay. So now let's solve a couple of examples under surface tension. So let's look at this first example. The surface tension of water in contact with air at 20 degrees centigrade is 0.0725 the droplet of water is to be 0.02 Newton per centimeter squared, greater than that of the outside pressure. So calculate the diameter of the droplet of water. A very simple question. So what they have given is the surface tension of water. So what is given to us is, if we write down the given details, the surface tension of water that is given as 0.0725 Newton per meter. And they have said the pressure inside the droplet that is going to be 0.02 Newton per centimeter squared. So that is going to be 10 to the power minus 2 the whole squared in the denominator if I have to convert it to Newton per meter squared. So it is 10 to the power minus 4. When taken to the numerator, it is 0.02 into 10 to the power 4. So that makes it 200 Newton per meter squared. Now, what they have asked us to find out is what is the diameter of this droplet. Just now we have seen that your pressure P is going to be equal to 4 sigma by D if it is a water droplet. So let's cross check that. So that is the surface tension in case of the liquid droplet. So P is 4 sigma by D. To find out the value of the diameter. So it is 4 sigma divided by the pressure P. So it is 4 multiplied by 0.0725 whole divided by 200. So let me use the calculator over here. So it is 4 times 0.0725 whole divided by 200. So that is 0.00145. Meters, or it is 1.45 millimeters. Okay, so that is what is expected from us in this particular problem. So let's move on to the next example over here. Find the surface tension in case of a soap bubble. And they have said the diameter of the soap bubble is 40 mm. And so this is going to be inside is 2.5 Newton per meter squared above the atmospheric pressure. And now they want us to find what is the corresponding value of sigma. So we know that for a soap bubble, P is going to the value of the sigma over here. So it is pressure is 2.5, diameter is 0.04, and this has to be divided by 8. And so let's use the calculator again. So it is 2.5 multiplied by 0.04 whole divided by 8, and that is 0.0125 Newton per meter. So this is the answer that we get for the surface tension in case of a soap bubble. A very, very simple problem here. Now, the next question is the pressure outside a droplet of water of diameter. So this is again droplet of water. So the diameter of the water droplet is given as 0.04 mm. So that is going to be 4 into 10 to the power minus 5 meters. And the pressure outside is 10.32 Newton per centimeter squared atmospheric pressure. Calculate the pressure within the droplet. So what they have given here is the atmospheric pressure. The pressure within the droplet is what we are supposed to find out, and the surface tension is given as 0.0. Okay, and so this is the water droplet again. We know that pressure P is going to be equal to 4 times sigma divided by D. So it is 4 times 0.0725 whole divided by 4 into 10 to the power minus 5. So I'll be able to cancel out these two. So what we have got is 7250 Newton per meter square. So that is the intensity of pressure inside the soap bubble. So the water droplet. The intensity of pressure is going to be 7250 Newton per meter square. Okay. So we will stop here and we will continue in the next section.